we go. Okay, so ladies and gentlemen, I'd like you to go to the model. You should have something like this, except you will see that I've added something called initial count infective, which we'll be manipulating. So this is going to allow us to change the number of people that start infective. And I'd like you to add it to the model. What you do to do that is you go to the system dynamics area, go to parameters, drag down initial count infective. Its default value will be 470. And then for susceptible and infective, we're going to modify the initial state to depend on this. For susceptible, the initial value will be 200,000 minus this value. And for infective, the initial value will be initial count infective. What am I doing by those changes? Anyone? Why am I subtracting it off here, 200,000 minus this, whereas this one, it's just the value of this variable? What am I keeping constant?
The total population.
Total population. I don't want to skew things by having more people start infective that we're going to have more people in the whole population. I want to keep constant the total population. Very common in this sort of modeling to want to make sure that a change really only affects one thing at a time. Here, my interest is affecting what fractions start infective. And one way to do that is to start infective will be this initial count infective. And here, it's 200,000 minus it. So the total will be what? Between these two will be, if I sum these up, it will be what?
Total population.
It'll be, yeah, 200,000. Okay. Ladies and gentlemen, you'll notice that any logic puts dotted lines here and, between this and the value. I dragged over links to link them up, but it turns them into dotted lines to indicate it's an initial value relationship. This relationship is just determining the initial value of the stock. So that's initial count infective. That's one change I'd like you to make for this. The next change I'd like you to make is, and it's the final one till we can start exploring this, will be I'd like you to make the mean immunity duration 275 hours. I had said 270 days, and I realized I screwed up. So let's just make it 275 hours. Okay, that will allow me to demonstrate it most directly. Okay. So again, two additions. Initial count infective, hitch it up to a susceptible and infective, and subtract it off from number initially susceptible, add it to the number initially infective. Its initial value is 470. And then secondly, mean immunity duration should be 275 hours. Okay, having done that, we can go and, any questions on that? Okay, I'd like you to go to baseline, and I'd like you to make sure the count of healthcare workers is set back to its default value, just so we can have a point of reference. The default value for it is 30. So in the baseline, the kind of reference scenario, the scenario against which we'll compare other results, I'd like you to set it to 30, okay? And you'll notice that it's initially bold, which means it's a different value. But if you set it back to 30 and you kind of leave it and come back, you'll notice it's no longer indicating it has changed. It just says 30. Okay? Okay. So, ladies and gentlemen, we are going to experiment with this model. Having added this so we could have more people start infected, and having made it so that we have a mean immunity duration of 275 hours, I'd like to run the baseline. So here we are. We're going to run it, and I am going to just run it at full tilt using this virtual time button, and we see it run out. Now, what's going on here? Can anyone narrate what's going on? I would remind you that the number effective is shown in red. Can anyone give a kind of story about what's happening here? You might want to look at the value of this duration of infection, too. So what's going on? What's happening at the initial start of the model? Well, let's run it in slow-mo. right? We have that option. So here we'll go run this, and I'd like you to keep track of this duration of infection. It starts as 13 hours, 14 hours. What's going on with this duration of infection for the first part of the model? Well, ladies and gentlemen, people are waiting longer and longer for treatment. It's going up and up and up. It started at 12, and now it's gone up to 930 hours, okay, with 30 healthcare workers. Okay, let's keep on going. And you see that it rises till it's remarkably high rates, and there it plateaus at very high levels. Why is it? Oh, okay, now it's coming down. Okay, between 230. It's going down very, very slowly here. Okay, we could watch it and we could let it run full tilt, and what we'll see is it will go down to an equilibrium value of about 3,054 hours, which is a long time to wait for treatment. Wouldn't you agree? Yeah. Okay, ladies and gentlemen, this is the duration of infection. So what's going on that leads to this really high rate of infection? What's the story here? Why is this rate of infection so high? Why do we have almost everyone in the population infected?
The recovery rate is capped by the number of healthcare workers?
Good. The recovery rate is capped by the number of healthcare workers. And because there's a very limited number, what happens to the duration of infection? Well, it starts low. Why is it going up initially? Because there's a waiting line, right? People are ahead of us, and so we're waiting longer, and therefore we're infecting more people. Think about us coughing in line. Think about us infecting people at home, or we're waiting to get our appointment. And we're waiting days for our appointment, and meanwhile we're infecting lots of people, and so the infection stabilizes at very high levels. And so I like Janelle's, that was Janelle? Yes. Okay, so I'd like to build on our suggestion. So let's copy the baseline, and ladies and gentlemen, let's paste it in, and I'd like to instead create a scenario where we have initially let's make it 45 healthcare workers. Okay? What do you think the impact of this will be? So we give it that name, and then we have to go change the value here, right? Count healthcare workers to 45. What do you think the impact of that is going to be? We've upped the number of healthcare workers by 50%, ladies and gentlemen. Okay, it's going to reduce the waiting time. How do you think that will yield outcomes in terms of the fraction infective?
The infected will stabilize at a lower...
Okay, it'll stabilize at a lower value. And just to remind you, with the baseline, we could go here, and it's a pretty easy math calculation, so we can do it. It's stabilized at about 182,000 infectives, right? Or something like, that's out of 200,000, right, people. So it's something like 91% of the population, 91.5% of the population. This is just about 183,000. Okay, 91.5% of the population or so. Let's go to initially 45 healthcare workers. How much do you think we brought it down? We increased the number of healthcare workers by 50%. We summoned people from all around the province to treat the afflicted in Saskatoon. So it went down to 174,000, which would be something like 87%. 50% more healthcare workers, and it went down a bit to 87%, right? Rather than just over 90%. Okay? Let's up it again. So let's do that same copy. We'll copy this initially 45, and we'll paste. Notice that I'm not going and modifying the model directly. I'm modifying the experiments. The experiments capture my scenarios. If you go and you modify the model, you could forget to change it back. Changing the experiment, these settings in the experiment doesn't modify the model. You don't have to worry about changing it back. So instead of making it 45, I'm going to make it initially 60. Ladies and gentlemen, that's twice the number of healthcare workers as in the baseline. Do you think that will have the infection from the infection prevalence, the fraction of people that are infected from the baseline? What do you think it will do? Do you think it will have it? What do you think? Okay, why speculate? Let's let the model do the calculations for us. That's what computers are good for. Doing lots of stupid things over and over again just to simulate this, right? Okay, now it's at 165,000. So we have something like 82.5% of the population now infected, with twice the number of healthcare workers. Ladies and gentlemen, we have not halved the fraction of infection. We've reduced it from just over 90% to just over 80%. Twice the number of healthcare workers. This is no nonlinear model. You still see we're going up in state space to an equilibrium value that's way up here. Lots and lots of people infected. Okay, ladies and gentlemen, let's raise the bar yet further. Let's muster everything we can. Import healthcare workers from Manitoba, from Alberta. Bring them in, fly them in from Ontario. Okay, here we go. We're going to have initially 75 healthcare workers. Okay? Count initial healthcare workers. Okay? Anyone want to speculate? What's that going to bring it down to?
There's barely any more healthcare workers.
Okay. Barely any more?
Barely any more, yeah.
You mean any more left? Yeah. Okay, so here we go. Let's okay, what's going on now?
Oh my God. What was the magic number?
Let's go find out. Get something closer. So, ladies and gentlemen, what did we just see there? Parse what we just saw.
The infection was wiped out before it ever had a chance.
Okay, the infection was wiped out. Notice what the duration of infection is. I said it started at 12, but I was off. It looks like it started at 5 was the baseline, the time, basically the time until treatment. Notice that that doesn't budge. So what's going on here that's different from what we saw? Why is it that this is almost no one infected?
There's probably a number where there's cube rows, and it's somewhere between 60 and 75.
Good. Once you start to have beyond 60 and 75, you're going to start to have a number of new infections that's going to exceed the what? Recovery, right? So infective is going to go up, and that's going to lead to this be higher and higher, which will lead to slower and slower recovery, which leads to more infections. Somehow there's a magic number between these two, a critical threshold, a tipping point, ladies and gentlemen, which is going to allow the recovery rate to outpace the number of new infections and to us to stop the infection from spreading. So let's copy this again. Let's go find something closer to that magic number. Let's look at, what do you think? Let's do a binary search, right? 60 plus 75 is 135. And so half of that is something like 67, right? It's about halfway between. So let's say 67 healthcare workers. Okay? 67. Okay? And let's put that in. Okay? 67 healthcare workers. What do you think? We got something halfway down from the 82.5%? Let's run it. 67, ladies and gentlemen, we're dealing with thousands of hours of waiting time per patient and a fraction infective that's about 80.5%. Okay, big difference between 67 and 75. Let's have that difference again, right? So it's a difference of about 8, right? So we'll add 4 to it. So let's do 71. Okay? This is building on the Rowan suggestion. Okay, so let's copy it. Copy, paste, and let's try to zero in on what this is, or at least roughly. So not 67, let's make it 71 initial healthcare workers. 71, ladies and gentlemen. 71. Okay? Okay, let's build it. What do you think is going to happen now? Ladies and gentlemen, we snuffed it out. Somewhere between this 67 and 71 is this tipping point, this magic point where we're able to get it to never take off. The recovery rate is greater than the number of new infections. The basic reproductive constant is what? Less than 1 from the start. People aren't starting infected. Okay, so that's pretty nifty. Suppose, though, we do something a little bit tricky. We copy that 71, and we go up and paste it in. And we do 71 healthcare workers, and we say 600 initially affected. What do you think will happen now? Initially, okay, I'm not spelling very well. Initially infected. Okay? Okay, 71 healthcare workers. We're going to start with 600 initially infected. What do you think is going to happen now? Think the 71 will be enough? Okay, now we're back to square one. Now it takes off. It's very sensitive to how many people are initially infected. Why? Give me an intuition. Because if we have more people initially infected, what's going to be going on?
More people will be around, more people that are infected.
Yeah, they're going to be waiting longer. Think about the last few straggling in. They're going to be waiting a long time. They're going to be infecting lots of people. So it's not so much just the number of healthcare workers. It's the ratio between that and the number of people infected. But you see the point that there's two equilibria here. If we start with more people infected, it'll go up to, at the start, it'll go up to this equilibrium. If we start with fewer people initially infected, it will peter out. We saw that just a moment ago with 470 people. So it's sensitive, ladies and gentlemen, yes, to parameter values, but more to the point, and more uniquely to this model from the ones we've seen, it's sensitive to the initial conditions, to the state of the model. And this is why I say, like Rowan pointed out, you have two different equilibria that you can go to with the same parameter values. These differ, ladies and gentlemen, only on the initial state, not with respect to, you know, the mean time that people have immunity or how quickly they get in, how quick or the number of contacts per person. Instead, just the initial state. If you start with a small enough initial state, it will peter out. It will go to a state where everyone ends up susceptible, no one infective. On the other hand, if you start too high, it'll go to the state up here, the state where you have a large number of people infected. So, ladies and gentlemen, that's a tipping point. And in terms of the state space, it will reflect kind of a line here in state space where it's in two different basins of attraction. We can think of this, and note that phrase, basins of attraction. These are like catchment areas. These are areas where like water will collect and go down to a lowest point. This is kind of the resting point here, the lowest point here. It's like this is one side of the Rockies and this is the other side. If we let a little drop of water, if we roll a marble here, it'll go down to this point. If we roll a marble on the other side, it will go to this point here. There's two different basins of attraction. We have this thing attracted to this attractor, this equilibrium point here, and it can go to this other attractor there. Now it turns out, we're not going to look at it for this example, but these attractors don't have to be points of total stasis. There's a notion of a dynamic equilibrium, which sounds bizarre. But the point is, in a dynamic equilibrium, that you actually go not to a fixed point where everything's in balance, you go to a limit cycle around it. You circle around it like a planet around a star, just sort of having a certain oscillation. And you can get those in these models as well. But the point is, here, depending on our point in state space, we can go to two different destinations. And if you think about a situation like this, they're commonplace. I mean, I would argue that in software development, you have these two different outcomes for software projects. You can have the same team, the same basic skill sets and so on, end up in a good situation or a bad one depending on managerial decision making or depending on the amount of work that's placed to them. And much of your goal as a manager of a software development team, as a lead, might be to try to nudge the situation from one basin to the other. You're trying to bring it across this divide. And just a little bit more investment may lead you to be able to bring it down here where the infection dies out altogether. Just a little bit more effort at the right time, boom, you switched it over between basins of attraction. But I'd like to highlight one other feature of this model before we get into agent-based modeling for the balance of the session. Ladies and gentlemen, I'd like to take a look at this model, and I'd like to do something we haven't done before in this class. I would like to take a look at the palette, and there's an area at the palette that's called controls. Okay? Now, those of you from computer science background will recognize the controls here are referring not to control theory, but to widgets that we can add to the model. User interface controls, as we call them. Things that we can add to the model that allow a user to control elements of the model interactively. I'd like to drag in a slider to this model and slide it will. So here we dragged in a slider, and I'd like to give it a name worthy of its function. So this is going to be called count HCW for slider. HCW standing for healthcare worker. So what did I do? I went to the palette that it says OK, and I'd like to drag in a slider. Okay? Here we go. Here's our slider. I'll frob it a bit so it's a bit larger. And I call that count healthcare worker slider. Now, the key thing I want to do here, and I'd ask you to pay attention. In this case, it's even more important than the name to our immediate goals. I'd like you to press link to, and you can actually point to what you want, but I'm going to pick it from a drop down. I'm going to pick this thing that says count healthcare workers. Okay, so we're going to link this slider up to this parameter count healthcare workers. And that's going to allow us to frob, or perhaps more precisely tweak, the value of this parameter. Okay, ladies and gentlemen. So we are going to frob that, and I'd like you to set the value of this parameter. The minimum will be 0 as the default, and the maximum will be 300. So what do you think is going to happen as we frob this slider as the model runs? Anyone want to hazard a guess?
As we get closer to the tipping point, it will get lower, and like the percentage of people, it will get lower and lower until it gets the tipping point where it dies out entirely.
Well, okay, so you're thinking ahead. You're thinking a few steps ahead about the dynamics. What will this slider allow me to do? What's kind of the function of this slider? Yeah, it's going to dynamically allow me to change the parameters. Now, you may wonder, why do I want to do that? I mean, am I just having fun? Well, yeah, I am having fun, but this is not just having fun. It's not a desultory experiment. I'm actually going to use it to show an extraordinarily important phenomenon that I want you to be, with which I want you to be familiar. Okay, so I'd like you to go back to the baseline, and I remind you the baseline is 30 healthcare workers at the start. Note my comment, at the start. I'd like you to go run this model. Okay? Ladies and gentlemen, here we go, 30 healthcare workers. Now, ladies and gentlemen, we could go frob this thing and get it to go to a certain point, but I'm going to show you a better way to do this. The point is I'm going to start interfering with this, and I actually want you to run it so we can do controlled experiments. I actually want you to run it a certain distance out. And the way to do that is to actually press stop and to go up here, and you'll notice that up here in the upper left, you could actually set, by pulling this down, you can say run for a certain number of time units. And I'm going to set this to run for 250 time units, okay? You see that? Up here, okay? And what I'm going to do is I am going to go now, and you can see here I will say run for. So I pull this down, having pulled in 250, I'm going to say run for. Boom. And now it's running for that. And I could speed it up, but it will only run for 250 time units, okay? And you'll notice that it's running along till time 250. I can go switch to the model, and this is what I see, okay? 250 time units, the model has gone to this very high point of infection, okay? 250 hours in. Wow, infection spreads fast, unrealistically fast, in fact, given viral dynamics. That's okay. Okay, so ladies and gentlemen, we've run it to time 250. Now it's time to frob the slider. So I'd like you to take the slider, and I would like you to up it to 60. And you notice as I frob this and let it go, it'll actually adjust the count of healthcare workers. And it's not critical to be exactly 60. If you can get it near 60, 58 is fine, small 60s is fine. That should be fine. I'll make it 58. And then you could do this again. You'll notice there's this little red thing here, and I'm going to run it forward 250. What do you think will happen now as we do that? Well, it's going to come down. Do you think if I keep on running it forward, it's going to disappear? No, why not?
Because you have a bunch of infected people, and the queue isn't going to...
Good. Good. Okay, so ladies and gentlemen, what was the number we needed to wipe this out before?
In between 67 and 70.
Good. Let's give it the benefit of the doubt. Let's drag it up to around 75. Here's 76. How's that? You went a little bit above 75 if you wish to. Okay. Here we go. 76. Okay. Let's run it out. Let's watch the infection disappear. Right? What's going on? Is the infection disappearing? Is the infection disappearing? But I have 76 healthcare workers. That was enough to wipe it out. Remember that? We did this iteration. Why is it not wiping it out?
Because that wipes it out with the baseline number of infectives at 470 or whatever.
I couldn't have put it better. It wiped it out with the initial population of infected. It nipped it in the bud because that was enough healthcare workers to keep a lid on the outbreak when there were a small number of infectives. But are there a small number of infectives here? No, there's a large number. Okay, so let's up the ante. Pull out all the stops, ladies and gentlemen. Let's set it to 100 healthcare workers, more or less, okay? You don't have to worry about the exact. I'm going to set it to 98, maybe slightly over it. 100, okay, 102. Here we go. Ready? Is it wiping it out? Ladies and gentlemen, let's set it to 200. 200 healthcare workers, ladies and gentlemen. More than twice, well more than twice, what was needed to nip it in the bud earlier. Is this wiping it out? Is it wiping it out? 200 healthcare workers? Why are we seeing this?
Because the ratio is still high between the number of healthcare workers and the number of people affected.
Okay, so yes, it's true. We have many times the number of healthcare workers that were needed to initially keep a lid on it, but it's not enough because there's many times the number of infectives that we were dealing with there. Okay, 250, ladies and gentlemen. 250 people infected, just over. Is that enough to wipe it out? No. Okay, let's do 280, right? What's happened there? Sorry? That was enough. We reached, ladies and gentlemen, the tipping point. But the tipping point here in terms of parameter values was much higher than the tipping point if we started in the initial state. So the tipping point that was required here, somewhere around 270 healthcare workers, 280 healthcare workers, that allowed us to wipe it out. But that was many, many times what it was that was required in the initial state. Why is that? Because in the initial state, there's fewer infectives to deal with. Ladies and gentlemen, a stitch in time saves 9. If you could deal with the problem early on, head it off, you can do so with far fewer resources. 71 or so healthcare workers. If you allow the problem to grow and to get established, you're going to need many times that, right? 3 times, 4 times the number of healthcare workers or so. So wipe it out. This is an example of what's called lock-in. It's a lock-in effect. Once the system goes to an equilibrium, it's a lot harder to get it out than it is to head it off. And again, you think about this with a software project. Once it gets into a bad state, morale is down, the code base quality is really low, there's been lots of turnover, you have impatient clients who would otherwise be accommodating but have been waiting too long for delivery of product. Whether it's spread of infection or dealing with problems in software projects or dealing with competition in the commercial sphere, often, ladies and gentlemen, there's a lock-in effect where the system, what's needed to nudge the system from one of these basins of attraction to the other, to bring down a system from going to an adverse equilibrium where you have a high infection rate to instead bring it to a low one. It requires much greater effort once the system has already reached or getting close to that equilibrium than it does if you do it initially. A stitch in time will save 9. It's like you could, if you repair that early on and prevent it from blowing up, it's much, much easier. And there's a lot of situations like that in life, where if we can head off the problem, it's just so much easier to deal with than if we have to mop up after it's already a problem. Complex systems are full of situations like this. Things get locked in. They get established in a way it's very hard to budge. And this is an example of this. 70, 75 healthcare workers required to keep a lid on the infection. If we had them from the start, 3 to 4 times that to deal with it after the fact. 3 to 4 times that to kind of clean up the mess that has been caused. Sometimes those investments realize tipping points early on for a small fraction of the price of what's required later. So if we're thinking about securing economies, if we're thinking about securing more efficiencies out of a system, being aware of the dynamics is important, especially if there's tipping points. And be aware that if there's a tipping point, there are multiple tipping points, it may be much easier to go from one basin of attraction early on than it will be later. This is lock-in effects, and it's very common in complex systems. Locked in because once it's established, it's much harder to change than early on. You think about addictions, it's a similar thing, right? If you can head off addiction to cigarettes by avoiding, using them, it's much easier than dealing with it after the fact where you've been smoking for a while and you're addicted to nicotine. Lots and lots of cases like this around. And this model is a very simple model that exhibits it. Any questions about this? Yes?
So
Jesse?
for our tipping point there, would like 280 be the tipping point for 50,000 because it starts changing at 50,000, or would it be the tipping point from the start, from the initial value?
Yeah, this is a good question. So you're saying here, after some experimentation, we were able to successfully lower the number of infectives here to the point where just upping this further to something like 280 somewhat was able to lead to an extinction event in the number of people infected, right? We were able to bring this down to qualitatively change what was going on, to eliminate the infection from the population for all intents and purposes. And you're asking, was this tipping point somehow the right tipping point, once the infection was established in general, or was it specific to this particular point? I would say it's specific to that. Okay, I have to be careful here. I actually think that it is a tipping point which would apply. Let's try to answer this empirically. My recollection is from analyzing the system, and there's some beautiful mathematical analyses behind this, which can be readily done. If we get it to very high levels and then we bring it up to 286, my recollection is that it will also bring it down even from this point. So I'm bringing up to 284, let's say. Here we go. Okay. Oh, look at that. It's not. Okay. So either those extra 2 made all the difference, or my memory is off here. Okay, so I'm running it. Okay, and let's bring it up to, and I'm going to bring it up to 280. Okay, 290 to 290. Okay, fine. Boom. Yeah, so it does seem very sensitive around that point. It can bring it down even from this very high level here. It's enough to overcome the inertia of the system there. So 280, a little bit more, 290 to, I'm trying to frob it slightly, 286, 288. Okay, fine. So it actually, it's a tipping point that is not purely contingent on that value of 50,000. It can break it down even from here. So this is a tipping point that is somewhat more fundamental, even though we introduce it later. Is that helpful, Jesse?
Yep.
Lock-in, ladies and gentlemen. A stitch in time saves 9 down the road. Okay? Questions on that? Yes?
This model seems to ignore the fact that healthcare workers could potentially get sick.
Indeed. Indeed.
Wow.
Yes. And so, great segue. That's going to take us closer to where...
The model's getting complicated.
Yeah. So, ladies and gentlemen, let's suppose... I couldn't have asked for a better segue. I think that's why Cheryl was laughing there. Okay. Ladies and gentlemen, that was not planted. Suppose we wanted to keep track here of the number of healthcare workers who are, not only of the population members, potential patients who are affected, but number of healthcare workers who are potentially infected, who are in different states. What would we need to do to this model to keep track of those?
We could just say that, of the possible healthcare, of the possible healthcare workers, say we have 200. The current number of effective healthcare workers is that 200 value minus the portion of the population which is infected.
So we could assume.
That's kind of, sorry, that's not very...
No. You're expressing actually
like
fairly
the
well.
ratio of the...
Yeah, the point is that we could, one assumption might be a starting approximation that we'll assume that healthcare workers are infected and therefore unavailable at a rate comparable to the whole population.
Yeah.
So if for the whole population, 90% of people are infected, we'll assume a similar thing about healthcare workers. And how easy would that be to do here? What do we need to do that? Suppose we wanted to incorporate that. What do we need to do?
It would be pretty easy.
It would be easy. So what could you add? And where would you add it?
Well, we put in a variable the infected over susceptible, or infected over total population.
Which is called fractional prevalence.
Right.
Okay.
And then we multiply that by count healthcare workers to get the percent of healthcare workers. Sorry, we Fractional prevalence is like a percentage, right?
Yes, percentage, so like 90%. It'll be
Right.
like it'll be 0.9.
So,
say,
so if we
90%.
subtracted
Yeah.
count healthcare workers times fractional prevalence from healthcare workers,
Mm-hmm.
then we have our effective healthcare workers.
That's right. Yep. Or you could create, effective healthcare workers available, and that would be 1 minus the fractional prevalence times the number of healthcare workers, identical mathematically.
Yeah.
But it would be a little variable here. And that's a beautiful little idea. Now, that's based on an assumption, as all models are, and it might be a good first approximation. What's the what are some of the limitations of that assumption? It has the great benefit of simplicity, conceptual clarity, but what's something that smells a little bit fishy about it?
We would expect the healthcare workers to have a higher level of hygiene or something.
Yeah, well, okay, higher level of hygiene, but okay, you think about your average.
But they also work around all the infected people.
Yeah, exactly. The healthcare workers are like magnets for infective people. I mean, you think about your average susceptible, they're going around and a certain number of people around them are infective. Fair enough. But you think about a healthcare worker,
They're like around.
it's like everyone, well, not everyone, but lots and lots of people around them are infected. So this mean number of infectious contacts per hour for a healthcare worker might be much higher. So suppose we wanted to actually keep track of as a separate, so it's a beautiful idea, Rowan, and I have to praise you for starting with a conceptually simple, straightforward, and clear, initial approximation. But suppose we decided that, things are different enough about healthcare workers working in an environment with tons of sick people that they need to be represented. We want to keep track of the number of them. How would we do that how would we do it in a model like this?
Would we use another set of stocks?
Yeah, we could basically take the whole copy of this, make a copy of it. So now we'd have susceptible people in the general population and susceptible healthcare workers. Effective people in the general population, effective healthcare workers. Recovered people in the general population, recovered healthcare workers. Now, would those be solitudes? Would they be independent of each other? No. The evolution of how many healthcare workers is getting affected would surely depend on the prevalence in the other population. Probably some also on its own prevalence. And the people in the general population, would they have a high number of contacts with healthcare workers, the susceptibles in the general population? Probably not. They'd probably have very limited contact with the others. So there'd be some mixing going on between them, with healthcare workers being exposed to lots of people in the general population, but your average person in the general population being exposed to a limited number of healthcare workers. So we can represent that. And we wouldn't have this nice, pretty formula over here alone, but it would end up being something like this, along with what's called a mixing matrix, which would sort of capture how many of my contacts with my own group versus this other group. And there's some beautiful mathematics behind that. But fundamentally, when we boil it down, what we're going to have here is a situation where we need to duplicate these stocks and flows for another group. Suppose we want to keep track, so put that issue aside for a moment. Suppose we want to keep track of male and female. Maybe women will have somewhat different transmission probabilities than men. They're involved in somewhat different practices in terms of being careful around others, or maybe they have more contacts with others in certain cases, or less contacts. Maybe these parameters are different, but suppose we want to distinguish men and women in this model. Putting aside the issue of healthcare workers for a moment, how would we do that? So how would we distinguish fractional prevalence among men versus among women? What do we need to do?
Easiest way is copy it again.
Yeah, copy it again. Make a copy of it, right? Now suppose we want to keep track of healthcare workers, male, female, and general population members, male, female. What do we need to do there? How many times would it have to be copied?
Copy it like
4 times. It's like all combinations of them, right? Okay, now this is starting to sound expensive. Suppose we want to, maybe we want to capture the fact that individuals who are of a certain age category, like children, are more likely to mix with other children compared to mix with, you know, with older individuals. And maybe that really matters because certain infections concentrated in children. So there, what do we need to do? Suppose we had 17 age categories, 0 to 4, 5 to 9, 10 to 14, all the way up to 8 plus. What would we need to do there? How many times would we have to copy this model if we were just thinking about age categories? There were 17 of them. Yeah, we need to have 17 copies of this model. And then suppose we want to take into account gender. Okay, now we're multiplying this model, not just 17 categories, 34 categories. There's a combinatorics here, ladies and gentlemen. It's not just additive. You actually have to multiply the number of categories along each dimension of heterogeneity. This is about heterogeneity. We want to divide people up into categories. And to do that, the way is by copying the model. And as you can imagine, this is somewhat unpleasant. After all, we're going to be duplicating the structure. Now, fortunately, these frameworks make it easier than that would sound. So if we go and we take a look at this, and you go look at, say, recovered, or go look at susceptible here, you'll notice that there's a thing called array here. And you don't have to do it, but I'll just point out, if we do array here, we can actually end up specifying that we want to subscript this stock by some dimension. Maybe it's age. Maybe it's age and sex. Maybe it's age, sex, and occupation. You know, healthcare worker or not. But basically, we can actually impose subscripts. But fundamentally, what's going on beneath the covers? It makes it easier. You specify equations in terms of subscripts. It's quite tractable, and it doesn't explode visually. But what's going on beneath the surface is there's actually copies of the stocks being made for every possible category. And you have to specify mixing between those categories. So, you know, if I'm a young child, I'll have more mixing with other kids of my similar age. So there'll be a mixing matrix across those categories. Yeah?
So are we like treating them as vectors then?
Yes.
Okay.
Yes, exactly. Treating as a vector, or in fact as a matrix, if you're thinking about age and sex, for example. But yes, you're basically subscripting it by treating it as a vector of sorts. Okay? And so we'll have a whole bunch of susceptibles, and you know, if you think about the spread of infection, there might be a band diagonal structure associated with, you know, susceptible given age has contact with those a bit older and a bit younger, and so you'll have sort of a structure of the mixing matrix that exhibits sort of connectivity to nearby ages, but not to all ages as much. And you can define these elements with models like this, and in fact analyze them in terms of their equilibria, etc. But ladies and gentlemen, it starts to get awkward and challenging. Also, reasoning about this contact between infectives, or between people in the general population and the healthcare workers, can become challenging. So today, as we speak, we are going to explore a new type of modeling that's very well suited to capturing heterogeneity, that's very well suited to capturing structured contacts. Okay? And this type of modeling is called agent-based modeling. Indeed. So, ladies and gentlemen, clear the deck we will. File, close all. Do I want to save it? Yeah. Boom. I'll post it as I am wont. Incidentally, I did post this afternoon the notes from last time, the derivation, including with Xiaoyan's nice correction there. There's an extra tau placed in, which made it much more beautiful and much